Section 5 of the Concept of Nature by Alfred North Whitehead. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Space and Motion. The topic for this lecture is the continuation of the task of explaining the construction of spaces as abstracts from the facts of nature. It was noted at the close of the previous lecture that the question of congruence had not been considered, nor had the construction of a timeless space which should correlate the successive momentary spaces of a given time system. Furthermore, it was also noted that there were many spatial abstractive elements which we had not yet defined. We will first consider the definition of some of these abstractive elements, namely the definitions of solids, of areas, and of routes. By a route I mean a linear segment, whether straight or curved. The exposition of these definitions and the preliminary explanations necessary will, I hope, serve as a general explanation of the function of event particles in the analysis of nature. We note that event particles have position in respect to each other. In the last lecture I explained that position was quality gained by a spatial element in virtue of the intersecting moments which covered it. Thus each event particle has position in this sense. The simplest mode of expressing the position in nature of an event particle is by first fixing on any definite time system. Call it α. There will be one moment of the temporal series of α which covers the given event particle. Thus the position of the event particle in the temporal series α is defined by this moment, which we will call m. The position of the particle in the space of m is then fixed in the ordinary way by three levels which intersect in it, and in it only. This procedure of fixing the position of the event particle shows that the aggregate of event particles forms a four-dimensional manifold. A finite event occupies a limited chunk of this manifold in a sense which I now proceed to explain. Let E be any given event. The manifold of event particles falls into three sets in reference to E. Each event particle is a group of equal abstractive sets, and each abstractive set towards its small end is composed of smaller and smaller finite events. When we select from these finite events which enter into the make-up of a given event particle those which are small enough, one of three cases must occur. Either 1. All of these small events are entirely separate from the given event E, or 2. All of these small events are parts of the event E, or 3. All of these small events overlap the event E but are not parts of it. In the first case the event particle will be said to lie outside the event E. In the second case the event particle will be said to lie inside the event E. And in the third case the event particle will be said to be a boundary particle of the event E. Thus there are three sets of particles, namely the set of those which lie outside the event E, the set of those which lie inside the event E, and the boundary of the event E, which is the set of the boundary particles of E. Since an event is four-dimensional, the boundary of an event is a three-dimensional manifold. For a finite event there is a continuity of boundary. For a duration the boundary consists of those event particles which are covered by either of the two bounding moments. Thus the boundary of a duration consists of two momentary three-dimensional spaces. An event will be said to occupy the aggregate of event particles which lie within it. Two events which have junction in the same sense in which junction was described in my last lecture, and yet are separated so that neither event either overlaps or is part of the other event, are said to be adjoined. This relation of adjunction issues in a peculiar relation between the boundaries of the two events. The two boundaries must have a common portion which is in fact a continuous three-dimensional locus of event particles in the four-dimensional manifold. A three-dimensional locus of event particles which is the common portion of the boundary of two adjoined events will be called a solid. A solid may or may not lie completely in one moment. A solid which does not lie in one moment will be called a vagrant. A solid which does lie in one moment will be called a volume. A volume may be defined as the locus of the event particles in which a moment intersects an event, provided that the two do intersect. The intersection of a moment and an event will evidently consist of those event particles which are covered by the moment and lie in the event. The identity of the two definitions of a volume is evident when we remember that an intersecting moment divides the event into two adjoined events. A solid as thus defined, whether it be vagrant or be a volume, is a mere aggregate of event particles illustrating a certain quality of position. We can also define a solid as an abstractive element. In order to do so we recur to the theory of primes explained in the preceding lecture. Let the condition named σ stand for the fact that each of the events of any abstractive set satisfying it has all the event particles of some particular solid lying in it. Then the group of all the σ primes is the abstractive element which is associated with the given solid. I will call this abstractive element the solid as an abstractive element, and I will call the aggregate of event particles the solid as a locus. The instantaneous volumes in instantaneous space, which are the ideals of our sense perception, are volumes as abstractive elements. What we really perceive, with all our efforts after exactness, are small events far enough down some abstractive set belonging to the volume as an abstractive element. It is difficult to know how far we approximate to any perception of vagrant solids. We certainly do not think that we make any such approximation. But then our thoughts, in the case of people who do think about such topics, are so much under the control of the materialistic theory of nature that they hardly count for evidence. If Einstein's theory of gravitation has any truth in it, vagrant solids are of great importance in science. The whole boundary of a finite event may be looked on as a particular example of a vagrant solid as a locus. Its particular property of being closed prevents it from being definable as an abstractive element. When a moment intersects an event, it also intersects the boundary of that event. This locus, which is the portion of the boundary contained in the moment, is the bounding surface of the corresponding volume of that event contained in the moment. It is a two-dimensional locus. The fact that every volume has a bounding surface is the origin of the Dedekindian continuity of space. Another event may be cut by the same moment in another volume, and this volume will also have its boundary. These two volumes in the instantaneous space of one moment may mutually overlap in the familiar way which I need not describe in detail, and thus cut off portions from each other's surfaces. These portions of surfaces are momental areas. It is unnecessary at this stage to enter into the complexity of a definition of vagrant areas. Their definition is simple enough when the four-dimensional manifold of event particles has been more fully explored as to its properties. Momental areas can evidently be defined as abstractive elements by exactly the same method as applied to solids. We have merely to substitute area for a solid in the words of the definition already given. Also, exactly as in the analogous case of a solid, what we perceive as an approximation to our ideal of an area is a small event far enough down towards the small